Last but not least, we're going to look at this epoxide ring opening, but this time in acidic conditions. When you have a weaker nucleophile, the epoxide is simply not electrophilic enough to react. So you expose it to acid and protonate the oxygen here. And what that's doing is by having this positive charge on the oxygen, you're actually pulling electron density away from the neighboring carbons, and so you've just made these even more electrophilic. We're going to see that's a strategy that's used fairly often in different contexts to protonate an oxygen, for example, to make the neighboring carbon more electrophilic. Now the weaker nucleophile will come in and attack, the ring will open up, and you end up getting this substituted alcohol. In terms of regiochemistry, the nucleophile is going to actually go to the more substituted side in this case. The reason for that is as the nucleophile starts to approach the electrophilic carbon and you start to form a bond here, this bond here starts to break, and the electrophilic carbon starts to bear a lot of positive charge. It has a lot of delta plus character to it. And it is more stable for a more substituted carbon to have a positive charge, or at least a partial positive charge on it. So it's more favorable for the nucleophile to approach that side, the more highly substituted side. In terms of stereochemistry, it's no different than opening in the strong conditions. It comes in from underneath, and so you end up taking whatever group is here and just flipping it up. Of course, since this was an equally substituted epoxide, then we also have to account for the attack on the other side and show that group flipped up. So here are a couple of examples. This time we have methanol in sulfuric acid, and you can use tosic acid for this as well. And once this oxygen is protonated by the sulfuric acid, the methanol is going to come in from either side. It comes in from the opposite side of the epoxide ring, epoxide bridge, so to speak. So this time, since this is pointing down, the methanol, the OCH3 groups are going to be pointing up. Just like when we learned a neutral nucleophile is used for, say, SN1 reaction, there's a final deprotonation step where that initially charged oxygen, so it comes in like this, then there's a proton transfer to get to the neutral OCH3 group. And anytime we use a neutral nucleophile, if there's an acidic proton that can come off at the end, it will to give the neutral product. And then finally, let's look at one that's not equally substituted. This time, because we're in acidic conditions, it's going to approach the more substituted side. This oxygen here is going to stay in the same position, but it turns out it's not on a chiral center, so it doesn't matter. The group that attacked came in from underneath, so it's going to be pointing down, and then here are its two carbons that it's carrying with it.